All right, everyone. Welcome to the colloquium this week. I'm pleased to introduce Levent Tuncel, who is a professor here in our department, as I'm sure everyone knows. So I don't know what else to say, so please just get right to it.
Yes,
Thank you
very much. Thank you very much, Sam. I'm indeed very grateful to have a chance to speak to you all. And I hope that I'm not overstaying my welcome by talking about something very technical. I really had this urge to talk about this new result. And if you're here to see a talk that adheres to the principles of giving a good mathematical talk, I'm very sorry, this is not it. There is a brutal amount of notation, incredible amount of definitions, and we're going to jump all over the place, and some of it will not be in a pleasant way. But indeed, there are some non-trivial results that I'm so excited about that I need to talk to you. So in short, these results are about, ultimately, they improve the computational complexity of certain nice primal dual algorithms for convex optimization. So that's like a tangible statement, not all algorithms, some special algorithms. And those algorithms have the property that theoretically they are some of the best in terms of their mathematical properties. But they also have this Goldilocks type of feature. In practice, the algorithms that are successful, interior point algorithms that are successful for convex optimization have these features. So it's really the kind of thing that you want to understand really well, regardless of your interest being in extreme theory or extreme applications. So strange place. So this is joint work with Joachim Dahl from Cardinal Incorporated and Levent Vanderberg, who's from UCLA. All right, we'll start gently and start explaining what the elements of the title of the talk means. So I'll call a cone regular if it is a pointed closed convex cone with non-empty interior. So I could say a cone is the kind of subset of the Euclidean space that is closed under multiplication by a non-negative scalar and under addition of elements. So it looks like this in R3. Okay. All right, pointed means that it doesn't contain whole lines. So indeed, it has a vertex when it's not empty, and that vertex is the origin in the space that the cone lives in. Okay, so when a cone is regular, well, I can always, given any set, I can write the dual cone of that set by simply taking all the elements in the dual space that make non-negative scalar product with everything in the set K. And the original set K is a regular cone if and only if it's dual. It's dualless. Okay, great. We'll talk about these things. So the convex optimization problems, we're gonna look at convex optimization problems in conic form. So my data is a linear map A and the vectors B and C. So the data is ABC. And K is a regular cone that defines the set of problems, convex optimization problems I'm interested in. So given data ABC, I want to determine if this has a feasible solution. And if it does, I want to find an optimal solution and so on. In any case, I want to certify my answers. And this is really without loss of generality when you talk about convex optimization, because any convex optimization problem can be put into this conic form. So what I mean by a convex optimization problem in Euclidean spaces, I mean the problem of minimizing a convex function over a convex set. Okay, so it's by adding an additional variable, it's not hard to make the objective function always linear. And once you have done that, all you have to do is remember this picture. You go to one higher dimensional space yet, and then you put your set over here on a hyperplane, and then you take the smallest convex cone that contains this, and that's your cone. Okay, so you can do this algebraically. Oh, by the way, we're going to go fast if you like speed. If you don't like speed, ask me questions that will certainly slow me down. Great, great. And we'll repeat some things, like, say, dual cone. So now so what I'm going to do is, now I'm going to tell you about a hierarchy of convex optimization problems graded with respect to the cone that you use, okay? So a cone is homogeneous if every pair of interior points that you can find a linear transformation that keeps the cone the same, but maps one point to the other. So in that sense, under these linear isomorphisms that keep the cone the same, every interior point is the same. Hence the name homogeneous. A cone is self-dual if you can find a scalar product under which, inner product under which k is equal to k star. So some examples, for instance, non-negative orthant is both homogeneous and self-dual, because you can take any positive vector in Rn, and then you can scale each entry so that the resulting vector is vector of all ones. And that positive scaling itself preserves the non-negative orthant, right? Now I showed you how to map anything to vector of all ones. I actually proved that that's homogeneous cone, right? Because if you know how to get to MC building from anywhere in the Waterloo region, then you know how to get from anywhere in Waterloo region to anywhere else. Good. And it's self-dual. It's self-dual, that's also easy to, and also the same is true for the cone of n by n symmetric positive semi-definite matrices. So you might want to keep those examples in mind for cones that are homogeneous and self-dual, and those cones we call symmetric. They're symmetric with respect to two notions. Great. Okay, so this tells us some cones. So now let me illustrate a hierarchy of convex optimization problems. If your cone is a polyhedral cone, then you have linear programming problems. In fact, it suffices to take your cone to be the non-negative orthant. And if your cone is a direct sum of second-order cones, we'll define pretty soon, then you have what's called second-order cone programming problems. These are more general. And if you take your cone to be n by n symmetric positive semi-definite matrices or their direct sums, that gives you semi-definite programming. If you take your cone to be a homogeneous self-dual cone, that is including everything actually, that's called a symmetric cone programming. It's more general than everything else. And if you remove the requirement that your cone be self-dual, it's only homogeneous, then you move to a larger class of cones. Those are homogeneous cones. And then there's another class we'll talk about, those cones that are called hyperbolic cones or hyperbolistic cones that come from stable polynomials or hyperbolic polynomials. And that's yet more general. And the most general set is the arbitrary convex cone, so it's convex programming. Is that okay? So this kind of hierarchy. But so then we have got these convex optimization problems. We formulated them in this nice conic form. But I see Steve is bored. This is not, we didn't gain anything. We need to introduce more structure. So now we want to have a nicer formulation. So we are going to have an analytic formulation that is nicer somehow. So this comes from a fundamental work of Nesterov and Nemirovsky that's more than 30 years old, where they prove that every convex cone admits a reformulation via the domain of a convex function. Okay, so what are the properties? The function is convex, 3 times continuously differentiable. The domain of the function is the interior of your cone. So where your function is finite, that identifies the interior. Everywhere else, the function value is plus infinity. So once you have such a function, you can throw away the cone in your formulation, right? And it essentially makes your problem unconstrained, because cone constraints now are the most difficult constraints. The other requirement is that the second derivative of the function doesn't grow very fast. So the third derivative, which is the change in the second derivative, is bounded by the second derivative, right? So it tells you that the Hessians of these functions, which are positive semi-definite matrices, they behave very well. They are not unwily. And this is an easy thing to get, but I also want them to be logarithmically homogeneous so that when you multiply the argument of the function by a positive scalar, there comes out minus theta times log t. So this may seem little magical, but if you have a homogeneous polynomial, multivariate polynomial of degree, say, d, and you look at minus log determinant of that polynomial, that is going to be d logarithmically homogeneous. And that's also going to be a prime example later on. Great. So the summary is that now we can pass on to another formulation of convex optimization problems where there is a function f instead of the cone. And under mild conditions, the number of iterations required by some interior point algorithms to produce an epsilon optimal solution can be shown to be bounded by this number. So in each iteration, the algorithm solves a linear system of equations. Okay, that's the biggest work, and the size of that linear system is bounded by the dimensions of your variables. So these are the two complexity measures, roughly speaking. the logarithm of the accuracy and the square root of this parameter theta. Now, one of the nice things is that for every convex cone, there exists such a barrier function with this complexity parameter bounded by the dimension. So this is quite nice, but some convex cones admit barriers with thetas much less than this. So for instance, second order cone, regardless of the dimension, admits such a barrier with parameter 2. All right, so that's, so now we have this formulation in terms of just the function, convex function f that formulates the cone. And now I want to look at finer and finer properties of such barriers. You know, that technical thing that I talked to you about, the third derivative being bounded by the second derivative. Now I want something else in addition to that. I want this function to be concave, but maybe, I don't know, since you weren't scared with the third derivatives, let me write in terms of third derivatives. The third derivative of the function, which is a three-linear symmetric form, evaluated at any vector in the cone, gives you a negative semi-definite form. So that's why we use the term negative curvature. But if this is also not very pleasing, just think about the property that the Hessian of this function f maps the primal cone k into the dual cone. So there's a nice geometric condition that is essentially equivalent to this property. Okay, so there's an additional property that enforces some tighter relation between the primal and dual cone governed by this function f. Okay, so this is the restriction. Okay, nobody is screaming, so let us increase the notation and everything else. So there is actually an incredible notion, even though more technical. It's one of the most wonderful results about interior point methods due to Nesterov and Todd. They introduced what's called a self-scaled barrier function. This is indeed a finer refinement of the last thing. This says that for every pair of interior points, the Hessian at one of them applied to the other takes you to the interior of the dual cone. And in fact, it turns out that with this condition and the next, it implies that the Hessian of the barrier is an automorphism, is an automorphism of the cone, essentially. And the cone is self-dual. So this is the other technical thing that tells you that the conjugate barrier defined as this satisfies this property with respect to this vector. And it is a technical definition. I'm not going to bore you with it, but I'm just going to piggyback onto the previous difficult definition. And I'm going to say that a barrier is self-scaled implies that both the barrier itself and its conjugate have negative curvature. So clearly, this is a refinement of the previous one because I'm requiring the same property not only for f, but also for the dual barrier f star. Okay. So this is indeed very, very technical, but that already also implies that K is a symmetric cone. So Nesterov-Todd theory applies only to symmetric cones. So going back to our picture, so I'm gonna keep having pictures when things get very bad so that we can take a breath. So remember the hierarchy of the convex optimization problems graded with respect to the cones. And in parallel, I can tell you about the corresponding self-concordant barriers that they admit. So up to here, including the symmetric cones, we have self-scaled barriers for them. But we don't have self-scaled barriers beyond this line. Beyond this line, we have negative curvature barriers, at least up to here, including the hyperbolic cone programming problems. But I don't know how far that line goes. That's one of the open problems I'm going to reiterate. I know that these cones admit negative curvature barriers, and we know due to Nesterov and Nemirovsky's big theorem that any convex optimization problem, its domain will admit a self-concordant barrier. Is the picture okay? We need these general pictures to really understand where I'm going to get to with the technical results. Okay, so some examples. But it's really cheating. As I'm showing you examples, I'm going to make more corrections and more definitions. Okay, so consider the homogeneous polynomial of degree d in n variables. And let E be some vector in Rn. We say that this polynomial is hyperbolic in direction E if PE is positive. And for every x in Rn, the scalar polynomial p of x minus lambda e has only real roots. Okay, so this is related to stable polynomials, and you may have seen in some of your courses hyperbolic polynomials for some reason or another. There are great applications all over the place of these objects. They go back at least to 1930s to Petrovsky, where some deep work in PDEs initially gave rise to this. But since then, in combinatorics, it found incredibly powerful applications, for instance. Okay, so this doesn't seem like an example yet. It is an example. So let us make another example. Now, let me just define the corresponding cone, and then we'll make some examples. So suppose that I have a hyperbolic polynomial, hyperbolic in direction E. Then I know that all the roots are real. And those roots, we're going to call them eigenvalues of x. So they are indeed generalized eigenvalues in the sense that if your polynomial is the determinant of x, right, and take as E the identity in that space, this is exactly the eigenvalues that you know from linear algebra and matrix theory. So this is a generalization of that. And then I can sort them. I can sort them in non-increasing order. And then I can collect all the x's in the space for which all the eigenvalues are non-negative. That turns out to be a convex cone. And that's the cone that we call hyperbolic cone or hyperbolistic cone, defined by P, hyperbolic polynomial P, with the direction E. Another way of defining it, there are many. This multivariate polynomial P, that's homogeneous of degree D, divides the space, right? When you look at the variety of it, it divides the space into various chambers. One of those chambers, for instance, contains E. And if you look at the connected component of that is going to be a convex cone. It's going to be the same convex cone as this. Okay, so there are multiple ways of defining it. So now really the examples. So if you take this quadratic polynomial, and as your direction you take 1, 0, 0, 0, this leads to the second order cone. This cone is also known as Lorentz cone or the ice cream cone. Okay. If you take Drake sums of those cones and intersect them with arbitrary affine subspaces, you cover all second order cone programming problems. That's a generalization, strict generalization of linear programming. Okay. And if you take as your polynomial the determinant of x, where your space is then by n-symmetric matrices over reals, or Hermitian matrices over complex, this has only real roots in the direction identity, and this leads to the cone of symmetric positive semi-definite matrices. And when you intersect with arbitrary affine subspaces, it becomes semi-definite programming. Okay, great. Okay, I kept the simplest one to the end. So if you just take on R the linear polynomial x, then this has only real roots in the direction 1, and that leads to the non-negative ray. That's linear programming. Because you can take the direct sums of those cones, you'll get the non-negative orthant, intersect with an arbitrary subspace, you'll get an arbitrary polyhedron. Good, so this is a special case. So one of the nice connections to convex optimization is that if you consider the function minus log the polynomial, where you're in the interior of that hyperbolistic cone and plus infinity elsewhere, this turns out to be a self-concordant barrier. And its theta parameter is the degree of the polynomial P. If the multivariate polynomial has degree D, then this will be a D logarithmically homogeneous self-concordant barrier. Moreover, it has negative curvature. It's not any old self-concordant barrier. So it's the 1 degree refined one, and Güler proved it in 1997. So now I want to talk about duality. We are going to come back to all of these things that we discussed. Remember the dual cone. Remember the conjugate barrier. So now what I want to say about that conjugate barrier is that if F is a self-concordant barrier for K, then the conjugate is a self-concordant barrier for K star. And it has the same complexity parameter theta. So that is quite nice. And also the conic setup that we have, we can easily model it in a symmetric way under duality, conic duality. So my feasible region was the intersection of an affine subspace with my cone. So I can write the affine subspace as a given point in the affine subspace B. So I'm changing the definition of my B. And the linear subspace. So this linear subspace is the null space of A, right? And then that's my primal. And I can write my dual in the same way, where my constant vector for the right-hand side became the objective function vector. This one became the right-hand side vector. The subspace, I took the orthogonal complement, and I also dualized the cone. So, in fact, some of you who teach duality in optimization, you might say, why don't you teach this in 250? Well, to really compute like this, they should be able to get the linear subspace easily, and they should be able to compute the dual cone easily. So, no free lunch. Luckily, in big theory, we can do free lunch things. So one thing I want you to notice is that the format of both inputs to the both problems are the same. Okay, subspace, two vectors, and cone. Okay, so that is the null space. So I'm going to say that the primal dual algorithm takes as input a subspace, two vectors, and then some initial primal point, initial dual point. And here's a semicolon here, because these are convex cones. They're given to me by some oracle, maybe a barrier oracle for F, right? Self-concordant barrier. Or if you're interested in non-barrier algorithms, maybe it's a membership oracle or a separation oracle, right? So what I want a primal dual algorithm is that I want it to be symmetric under duality, which means that if the algorithm takes the input LBC, X0, S0, K, and K star, say that it gives the sequence of iterates XK, SK for the primal and the dual, when you give me the dual problem, right, instead of L, you give me L perp, instead of B, you give me C, and so on, it should just give me SK and XK. Just swap them. So that's the kind of symmetry that would be a desired property. Alone, it's not very meaningful. But another thing I want is what I would like to call scale invariance. If I'm getting for this input, if I'm getting the output, primal dual output XK, SK, this sequence of iterates, if I happen to apply an automorphism to my cone, then apply the dual automorphism to my dual cone, and then do the corresponding transformations in the primal and dual spaces, mathematically, I have not changed anything essential. So the algorithm should be invariant under that kind of automorphisms, so it should just spit out the automorphic maps of those iterates. Okay? So these are abstract definitions of a symmetric algorithm. Some crazy person came up with it. And I can say that, and you might figure out why. So it turns out that the Nesterov-Todd framework that we briefly mentioned actually gives you a symmetric algorithm in that sense. That's one of the very pleasing properties of that algorithm. And also, almost all successful software, for instance, about symmetric cone programming actually uses that algorithm, Nesterov-Todd algorithm. So to tell you about interior point methods, I have to tell you some notions. So one of them is the central path, and that central path notion comes from the barrier that we talked about. So once you have a barrier, you can take a parameter mu that's positive, and you can consider the family of optimization problems P mu, parameterized by mu, where you keep increasing the weight that you give to the real objective function and relatively reduce the weight that you're giving to the barrier. So you send mu to 0 to have this minimizers of this problem sort of approach the possible minimizers of your original conic optimization problem. And the thing is that this, actually the self-concordant barrier is strictly convex. This problem, assuming that there's a feasible solution that's interior, it will actually always have a unique solution. And that's a very nice problem because it's essentially unconstrained, because X being in the affine space is same as being in some Euclidean space, right? So it's an unconstrained problem. And you can do the same thing from the dual side with the dual conjugate barrier. You'll end up with the same same central path. So when you look at all the unique solutions that you get from P mu and D mu for every mu, that will create a path in the primal dual space, X mu, S mu, and that's called the central path. And then if you start with interior points interior to the cone and feasible in the primal and the dual, then this mu k will be the duality gap of that pair, and it will also correspond to that centrality parameter. And by reducing this mu k, you're going to approximate the set of optimal solutions by generating smaller and smaller mu k's for these pairs of interior solutions. So again, things got heavy. Let's draw a picture. So this is what I call a Mickey Mouse picture, in the sense that indeed this is a convex set, but I didn't really draw the central path by minimizing P mu for every mu. I just plotted it, okay? But it looks like that. So this is my feasible region, and C is increasing this way, so it's minimized uniquely at this point, and the central path that we defined looks like a curve like this in this small two-dimensional example. So what do the interior point algorithms do? They might try to stay close to the central path by generating approximately central points and converging to the optimal solution, or they can be more relaxed and they can use what we call potential functions or other criteria and just stay in the interior by balancing the distance to the boundary together with the objective function. Okay, so these ones are more practical than the ones that restrict to a boundary of the central path. Okay, so Nesterov-Todd had that beautiful theory, and they came up with the convergence analysis of a wide class of symmetric primal dual algorithms in that wild sense that I defined, that achieve this current best complexity for symmetric comprogramming. Okay, so, and the ingredients of such an algorithm are really cornerstones of best software as well. So this kind of, but the power of this result really spans a lot in theory as well as in practice. So I was excited about that, and I introduced a generalization of those algorithms to all convex optimization problems. So in doing so, I proposed a complexity measure for such generalized algorithms. So what this does is that it looks at these positive definite symmetric matrices that for given primal X and dual S, these are the iterates of, say, your algorithm, it tries to find a positive definite symmetric matrix T so that T maps X to S. It maps the gradient of the conjugate at S to gradient of X, and then it satisfies the sequence of these Lerner inequalities. So this means that T minus the left-hand side is symmetric positive semi-definite. So this is the Lerner order, which tells you that the difference of two of those symmetric matrices is positive semi-definite. Okay, so this sounds like an insane thing to find such a thing, and this delta F is some kind of a proximity measure. There's a complicated formula for it in terms of X and S and images of X and S under the gradient, but it is the kind of quantity that's always non-negative, and it measures how close you are at XS to the central path. So these are some linear equations on T, because for a given X and S, X is constant, S is constant, these gradients are constant, and the Hessians are constant. So this last constraint is what you would call a generalized eigenvalue problem. It's about computing some kind of generalized eigenvalue of these two matrices, symmetric matrices. But then there is more complication with this proximity measure that's stuck in there, but that's what it is. And then you look at this, I'm trying to minimize Xi, so my variables are Xi and this transformation T. So this is really a semi-definite optimization problem. So if you got tired, many of you are, and then what you would have learned is that to solve a convex optimization problem with n variables using these algorithms that I generalized, you need to solve a semi-definite optimization problem where the variable is n squared by n squared in each iteration. And then you need to bound that Xi, because that Xi is going to be a complexity measure. It's going to figure into the number of iterations. Okay, so at that time, almost more than 25 years ago, I was able to prove this bound. So if you can bound Xi, then a wide class of primal dual interior point algorithms that have those primal dual symmetry-like properties, they satisfy this iteration bound, but there is this additional factor Xi of f. So when I reformulated Nesterov-Todd work in terms of this complexity measure, their main result essentially boils down to showing that Xi of f is at most 4/3 for every symmetric cone and every self-scaled barrier f. So somehow, the big part of the analysis boils down to solving infinitely many semi-definite optimization problems approximately and bounding the optimal value. And they did it with beautiful analysis. Moreover, they showed that they can find that T, that transformation capital T, as the Hessian of the barrier function evaluated at a point. So that's called the Nesterov-Todd scaling in that case. So this was the main result. So let me start with the first improvement. So now the new results are really starting. Thank you for bearing with me. I took that 4/3 and replaced it with this horrible thing. That's the first improvement. It's going to get worse, I promise. So, I mean, okay. So actually what I'm claiming is that this is the optimal value. Nesterov and Todd upper bounded this value. So this is the exact value. But come on, it's not nicer than 4/3 by any stretch of imagination. Okay. There's an additional thing. In addition to, so we can also show that Nesterov-Todd scaling actually satisfies being in that set for this value. This value is strictly less than 4/3. So that itself is a slight improvement. And there was another scaling that was introduced by a PhD student of mine in 2014. That integral scaling also is optimal in that sense. So that's also a new result. But let me just make this a little bit nicer first. So, in fact, I have to tell you that when we had this result, this wasn't the first formula for CF. The first formula was almost a page long. It was only a function of theta. This was a simplified version. And this is the further simplified version. So if you set tau to be theta divided by theta minus 1 square root, then this value is the arithmetic mean of tau and tau plus 2 divided by their geometric mean squared. So you can say it in words. But it's really crazy that you get these things in arithmetic and geometric means. So here's the sadder news even. So you can actually plot that function that gives you the optimal value of this proximity, the complexity measure. And Nesterov and Todd showed that this is bounded by 4/3, right? So you see that the improved bound I told you at, say, when the dimension is 60, it's already 1.33. So this is really an incredibly small improvement in terms of these values, right? But I think you see that there is some more understanding that goes into it. And the integral scaling, if you're wondering what that is, integral scaling is the integration of the Hessian along this line. So there are indeed numerical ways of computing this. This particular choice of T is also optimal for symmetric cone programming. That's maybe the more interesting newer result. But one of the things that this kind of new theory gives is that we can actually characterize what are the worst pairs XS, where this Xi, this complexity measure, is maximized. So those of you who are interested in the theoretical analysis, or just in the computation with interior point methods for, say, semi-definite programming or so, you should get nervous when you're getting close to the boundary because all kinds of things become ill-conditioned. And this key complexity measure actually doesn't. That's one of the things. So the worst pairs are these x1 hat, x2 hat, and x3 hat. So this is the case when I'm looking at the non-negative orthant in R3. I took a slice. The central point is some dual point in the interior of the dual cone. I took its image under the barrier function f star, f prime star, and I'm looking at the set of all primal points for which this dual point corresponding to this gives me the Worsk C. There are exactly 3 of them. And they lie on this red ellipsoid, which is, if you know what a Dickin ellipsoid is, it's like half of that Dickin ellipsoid. So it's really close to the central path. Not very, very close, but relatively close. The place where theoretical algorithms operate. Okay, so, and this actually, there's a more general theorem that characterizes all such points. Okay, but now this is the more interesting result. Actually, we're able to show that for every self-concordant barrier with negative curvature, we also have the same bound 4/3 that Nesterov and Todd had. Moreover, so at this stage now, we are beyond the symmetric cones. Symmetric cones are a special case, so there is no Nesterov-Todd scaling, but there is still the integral scaling, and it turns out that integral scaling is near optimal for those problems as well. So what is the improvement in the complexity bounds for these algorithms? So these are, if you know what potential reduction algorithms are, those are among those. So they don't restrict you to a small neighborhood of the central path, but they are more free moving. So for those algorithms, the previous best bound was theta to the 5/2 log 1 over epsilon. So this result improves it by a factor of theta squared. So if linear programming, say, theta is n. But in that case, we already know this bound. So this is for more general problems, say with negative, say hyperbolic polynomials with negative curvature and those things. So again, that's a lot of theory. So let me tell you about the picture again. Okay, so this is an example of maybe I should write something. So I gotta slow myself down. You're being too nice. Way too nice. It's not slowing me down, so I should slow myself down. So here's an example of a cone that is not symmetric. So it's actually neither homogeneous nor self-dual, but it admits a negative curvature barrier. So what it is in this case, well, it looks like Superman, uniform, right? That's intentional. It's a tridiagonal Toeplitz cone intersected with a hyperplane. So maybe I can just tell you about the cone. So in this case, the cone is defined to be set of all. So it's a 3-dimensional cone, but I'm going to define it by using a 5x5 matrix inequality. So I'm going to take so x1, 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 x1. So the same variable is on the diagonal. It's a Toeplitz matrix, x2, 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 x2. It's fun, right? And then x3, 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 and then zeros, zeros, and this thing is positive semi-definite. So again, my handwriting is horrible. My alignment is probably worse. So let me just make sure that it is a Toeplitz matrix. So you see that the diagonals are all the same variable x1. And the superdiagonal and the one right under is also the same. It's a symmetric matrix, right? And then the last one. And it's a banded matrix, right? So clearly this defines a 3-dimensional convex cone, right? Because it's, if you like, it's the intersection of the 5x5 symmetric positive semi-definite matrices with a linear subspace, right? So to get the Superman one, you need to scale x1 by square root of 5, this by square root of 8, and this by square root of 6. But mathematically, it's the same cone. It's just so this cone. So this is the hyperbolistic cone for the polynomial which is just the determinant of that 5 by 5 matrix. So the polynomial there is a degree 5 polynomial in 3 variables. And you know, we have a similar picture, and the worst points, there are exactly 2 of them. So this is not a Mickey Mouse picture. This is actually computed explicitly. Indeed, this is the slice of that cone with properly scaled with those square roots. And then these are various neighborhoods of the central path for that point. And the worst points attaining that xi are these 2. Okay, again, they are sort of relatively close to the central path. Okay, great. More theorems. So we also have theorems for general self-concordant barriers. Oh, yes, Henry, please.
So it's known that the Toeplitz matrices become very ill-conditioned when they get large. Where does ill-conditioning come into the complexity?
Exactly, a great question. So, as I was saying earlier, you know, if you're interested in software or practice or solving these problems with interior point methods, you always get nervous about getting too close to the boundary prematurely, or eventually you have to get there, so you worry about ill conditioning. And various things that you do numerically, they will get ill conditioned. But here I'm looking at something very intrinsic to the problem and the barrier, which is like a generalized eigenvalue of primal dual Hessians properly scaled with a proximity measure. So that's the striking thing. This deep measure never gets ill-conditioned. And the worst thing about it happens always near the sort of between something that's between the half Deakin ellipsoid and the full Deakin ellipsoid. It's always inside the Deakin ellipsoid, the worst points, not near the boundary. So that's another sort of new news about this result. And I'll say more. It's an excellent question. All right, great. So for general self-concordant barriers, we can actually bound, so I wrote it in terms of this generalized eigenvalue formulation. We can bound xi by 2 theta, and I used xi head check because in this theorem, we throw away the linear constraints in the definition of xi. So if you remember, xi had this horrible definition, and I want my t to satisfy these linear equations, you know, there are 2n of them, and these Lerner inequalities. So if I remove these equations, then I have a relaxation of this, and the resulting xi I call xi head check. So it's smaller than the actual xi. So that's closer to computing infinitely many generalized eigenvalues of Hessians and then bounding it, and we can bound it by 2 theta. So this was 4/3 for negative curvature barriers. In the full generality, the best we can do is 2 theta. But for the points that are away from the central path, this is some measure that tells you you're away from the central path, we can prove that for all convex optimization problems and all self-concordant barriers, this measure is bounded by 4. 4. It doesn't go to infinity or anything like that. It doesn't even go get near theta. So we can use that previous theorem and actually show that for general barriers, for general conic problems, this complexity measure is bounded above by 2 theta, and the integral scaling actually gives a possible solution t in that set. And this one for the general barrier functions improves the complexity of these potential reduction algorithms that are symmetric by a factor of theta. So for, say, n by n symmetric matrices, a factor of n. Okay, so talking about, you know, what this xi value is like locally, we can define the local version of that complexity measure for each xns, and then we can actually show that Nesterov-Tott scaling is also optimal for this localized measure. Once you have a primal interior point x and a dual interior point s, the best scaling you can find with respect to this minimization of xi is the Nesterov-Tott scaling and the integral scaling. So both of those are optimal. In case of linear programming, they become the usual diagonal scaling, both of them, both the integral scaling and Nesterov-Tott scaling become the usual diagonal scaling, primal dual diagonal scaling. So for self-concordant barriers, general self-concordant barriers, when you look at the pairs of points XS that are close to the central path, with Miklebus, we actually bound C by something smaller than 4/3. And that gave interior point algorithms that are primal dual symmetric with iteration complexity squared of theta log 1 over epsilon, but they follow the central path very closely, right? And Obro from Denmark in 2019, he proved that as long as X and S lie in what's called a half-Dickin ellipsoid, again near the central path, this C head check, the relaxation of it is bounded above by 3. And in one of the earlier theorems, I said that we showed that when you're closer to the boundary, this is bounded above by 4. So what does this really say? So let's go back to this Superman picture. So what it says is that when you look at this primal dual complexity measure that comes from these Hessians of F and the conjugate, inside this ball, in general this is an ellipsoid, the value is bounded by 3. And when you're close to the boundary, in this band, the shaded band, it's bounded by 4. So the bad points are actually between the Dickin ellipsoid and this smaller ellipsoid. And they're very close to this smaller ellipsoid. So it gives you some additional justification as why these primal dual interior point methods that are symmetric, that do so well in linear programming and STP, might do well for more general conic programming problems. So this result that's about negative curvature covers a large class of convex cones, including hyperbolic cones. And as a result, we improved complexity bounds for certain primal dual symmetric interior point algorithms by theta square and theta. But the following problems remain open. For symmetric cones, we characterized actually all pairs XS attaining the worst value of Xi. But I don't know how to characterize that for an arbitrary self-concordant barrier. Both for Xi and the relaxation of Xi hat check. And another thing I had mentioned earlier, I know that every hyperbolistic cone admits a negative curvature barrier, simply minus log of the polynomial. But I don't know if every cone admits it, or hyperbolistic cones are the only ones. So that's an open question. And regardless of that answer, we bound the C for an arbitrary self-concordant barrier by 2 theta, but there is no lower bound that I know that's larger than 4/3. So perhaps that 4/3 result that we proved for negative curvature barriers applies to all self-concordant barriers. I don't know the answer to that either. Of course, so the question 3, which cones admit logarithmically homogeneous self-concordant barriers with negative curvature, that was posed in a paper with Nesterov, but since then there has not been any development. Still completely open. And then a year later I posed a restricted version about just algebraic cones, namely convex cones defined by solution sets of multivariate polynomial inequalities. Whether those cones admit negative curvature barriers. If the polynomials are hyperbolic, then they do. But they may not be hyperbolic and still define a convex cone. In that case, I don't know the answer. And another line of research is related to characterizing these worst case pairs in terms of the properties of the barrier function and the geometry of the cone. So there's more that could be said there. And I have been jabbering about for 50 minutes. I'm so grateful to you for your patience to having sat through this brutal notation and stuff. I thank you very much.
Yeah, thank you for the talk. Are there any questions? Please wait.
Thanks for the very nice talk. I was wondering, as you're very well aware, a classic issue in the interior point literature is a proximity measure for the central path. Does this new analysis suggest new proximity measures, or?
Excellent question, Steve, as always. And you're a little too generous about the talk being nice. So, yes. So, I need to go back. I need to go back to the definition of this thing. So in defining these sort of good primordial scalings, there is this function delta f of xs that I called a proximity measure. So inside that definition, there's a quantity mu tilde minus 1. So mu is inner product of xs divided by theta. So that's the average duality gap. Mu tilde is the analogous thing with the gradients of those things. So you can prove that mu times mu tilde is always at least 1. And it is 1 if and only if x and s are on the central path. So that statement is a grand generalization of arithmetic harmonic mean inequality. So if you restrict yourself to the logarithmic barrier for the non-negative orthant, then mu tilde becomes the arithmetic mean divided by the harmonic mean of your iterate x. Well, xs, but they're properly scaled. And in case of semi-definite programming, that is the eigenvalues of x and a half, s, x and a half. So the arithmetic geometric mean, arithmetic harmonic mean inequality on that. So it turns out that this proximity measure indeed is critical. And another nice thing about this proximity measure is that when you look at these pictures, say look at this picture. So in this picture, this one is the Dickin ellipsoid. So this is the one that's defined by the Hessian of the barrier at that point. In this case, it turns out to be a disk, but it's an ellipsoid in general. You see what kind of an approximation it is to this outer figure, right? This inside one, that is the mu tilde neighborhood. It says that the points inside that curve satisfy mu times mu tilde at most 2. So if it's equal to 1, you're here. If you're less than or equal to 2, then you're in here. And you can see from this picture that indeed it approximates the geometry of the set much better than the Dickin ellipsoid, which is always an ellipsoid. So there are some, I mean, this is not a very sharp answer to your question, but I think it's an answer that shows you that there are some new proximity measures in addition to this complexity measure C becoming sort of more relevant. Thank you for the nice question.
Other questions? All right, let's thank Levent again.
Thank you.